In FTIR, infrared light energy is absorbed when the natural vibration of a chemical bond frequency matches with the frequency of an applied infrared light. It is important to mention that different types of bonds in a molecule absorb infrared light energy at different frequencies. And this fingerprint of absorption at different frequencies can identify or characterize the molecule. In simple terms, I could explain the FTIR. Molecules in a material are dancing, and the FTIR is the camera that records the dancing moves. Our eyes cannot tell the molecules in a material, however the FTIR machine can. It can see the visible vibration of the bonds in functional groups in a molecule. It is a molecular fingerprint scanner. I am going to explain more step by step. In this molecule, chemical bonds are holding atoms together. They are not rigid sticks. They are like springs. They are constantly vibrating at natural frequency. For example, stretching, bending, and wagging. I think you understand. I am talking about the vibrations of the molecular bonds between two atoms. I am explaining how FTIR works and what FTIR can solve. Consider one wavelength of light. We can measure absorption energy by a bond in a molecule. However, we need to know when. A bond in a molecule can only absorb infrared light if frequency of the light matches the frequency of the natural vibration of the chemical bond, that is resonance. From this vibration frequency and energy absorbed, we could identify the types of bonds present in the molecule. And then we could translate it to a material consisting of different types of molecules. In this diagram, we can see an infrared light source, a detector, and a bond with vibration of an atom. It is a stretching vibration. Then we can pass an infrared light through the chemical bond. What would happen? Either the bond can absorb light energy, or light could pass through the bond without causing any effect. We want to know when the bond can absorb energy. We know this bond can absorb light energy only when frequency of the infrared light matches with the natural vibration frequency of this chemical bond. FTIR measures the absorption energy at this frequency. I am going to explain more about this clearly later. How does FTIR works? In FTIR, we shine all wavelengths at once. It is done by an interferometer. There are many steps. An infrared light source emits lights at all frequencies. The components are sliding mirror, fixed mirror, detector, beam splitter, infrared light source, and a sample. The sliding or moving mirror precisely controls the optical path difference, that is OPD, between two beams of infrared light. First, IR light emits from the infrared light source, split into two. One beam passes to a fixed mirror and another passes to a sliding mirror. A beam splitter can split the beam into two. 50% goes to a fixed mirror and 50% goes to a moving mirror. These beams can bounce back and recombine, that is recombination and interference. Because one mirror moves, the beams travels different distances. When they recombine, they undergo constructive and destructive interference. This creates a signal called an interferogram. It is then directed through the sample. Interferogram looks like a complex wave pattern containing encoded information about every wavelength simultaneously. The beam then reaches to the detector to record the signal. The interferogram is a raw data and we need to decode it. The Fourier transform is a mathematical operation or tool that converts the signal from the time domain, that is what the detector can see, to frequency domain, that is what we can understand, that is absorption versus wave number. Time domain means intensity decays with time. Finally, we receive a spectrum as shown. It is a plot of absorption versus wave number. The spectrum provides a plot of absorbance in arbitrary unit as a function of wave number, that is centimeter inverse. The peaks indicate where the light was absorbed by different bonds. A spectral range typically 4000 to 400 centimeter inverse. The region of 4000 to 1500 centimeter inverse is considered a functional group region, and fingerprint region is considered from 1500 to 400 centimeter inverse. Fingerprint region below 1500 centimeter inverse contains unique complex patterns for compound identification. FTIR spectrum then can be used to identify a material by matching it from the spectrum available in a library. In addition, we could determine any effect of treatment on the material or any change caused by environmental conditions. Chemical reactions could also be studied. We could go through an FTIR spectra of encapsulated broccoli leaves. As discussed earlier, each peak indicates a specific chemical bond in the molecules present in the extract. An FTIR absorption band at approximately 3407 centimeter inverse is typically associated with the stretching vibration of an OH, that is hydroxyl bond, or an NH, that is amine or amide bond. What are the sources of these chemical bonds? An OH stress from alcohols or phenols that is involved in hydrogen bonding. It is usually appeared as a strong and broad band in the range of 3200 to 3600 centimeter inverse. An NH stress typically appears in the 3300 to 3500 centimeter inverse region. It is generally not as broad or intense as the OH band. Primary amines could show two bands in this region, while secondary amines show a single band. Presence of a carbonyl carbon-oxygen double bond peak around 1650 to 1760 centimeter inverse would suggest an amide or a carboxylic acid. An FTIR band at approximately 1602 centimeter inverse typically corresponds to one of several functional groups, and the most common ones are discussed in the next slide. The exact assignment depends heavily on the molecule being analyzed and the overall spectrum. What are the possible sources of this band? It could be aromatic, carbon-carbon double bond ring stretching vibrations, that is in polystyrene and phenyl rings. Carbon-oxygen double bond, carboxylic group stretching vibrations, particularly the asymmetric stretch in carboxylate salts or amino acid side chains. Other possible sources are amide I bands in proteins, which is primarily carbon-oxygen double bond stretches. carbon-nitrogen double bond, azomethane or imine stretching vibrations, carbon-oxygen stretching vibrations in certain specific contexts, for example in dextrin. I have just discussed two peaks. Other bonds could also be analyzed similarly from literature. In many instances, the interpretation of the bonds is challenging at its scales. The exact nature of the bonds is determined by the shape, intensity, and context of the peak within the full spectrum. In another video, I will explain more about the interpretation of the FTIR spectrum and different types of FTIR. Thank you for watching this video until the end.